get started. Welcome to the seminar in computer architecture. Today we will have two excellent presentations regarding processing in memory. And our first presenter, Solomon Thiessen, is a master's student of computer science in ETH. He's very interested in large language model related optimization. He's currently also working at Digital Twins. Please go ahead. Yeah.
For the introduction, so no worries. No worries. So yeah, like you guys saw, the title of the paper that I'm presenting on today is Processing in Memory, the Terasys Massively Parallel Processing in Memory Array. And yeah, it's Halloween, so I added some festivity to the slides. Yeah, bear with me for the animation. Okay, so let's start with an executive summary. Of note, this paper is more of a case study or like a technical write-up of a specific workstation. So yeah, you'll kind of see that reflected in the flow of the presentation. So the problem that the authors set out to solve is that serial processing can be slow compared to parallel processing, but SIMD parallelism is sort of application specific and may not always help. And therefore allocating hardware devoted solely to the purpose of SIMD parallelism may be wasteful. And so the goal was to build a PIM-capable memory array and achieve supercomputer performance on SIMD suitable workloads without sacrificing adaptability to other workloads. So the key idea, or kind of the contributions from the paper, are that they developed SRAM capable of acting both as conventional memory or a PIM array. And they created a high-level C-based programming language to interface with their PIM array. And in the end, the results they achieved were up to 50 times supercomputer performance for SIMD suitable workloads at 125 times less the cost. Okay, so here's kind of the outline of the talk. First, I'll give some motivation. Then we'll talk about the background, a little bit of chronology of the field of processing and memory. Then we'll talk about the specific hardware implementation, the high-level language, and then we'll discuss a little bit of the results. And then, yeah, I'll open the floor for questions, and then we can talk about the strengths and weaknesses, and I have some discussion questions prepared. So starting with the motivation, as I mentioned, so the authors perceive this serial processing bottleneck. And so, yeah, serial processing obviously takes more time for the same computation. And the more data you have, the more steps you need to take in order to process this data. Whereas with parallelization, you can compute more in the same amount of time, and you can scale to handle more data. Yeah. However, as the authors point out, not all applications are well suited to all kinds of parallelism, and so single purpose hardware shouldn't be allocated to specifically, in this case, SIMD parallelism. And then this is kind of the more modern and typical motivation for processing and memory today is, of course, the data movement bottleneck, which we are probably all familiar with. So 1995's and today's computing systems, as we know, are processor-centric, and this comes at great system cost. So moving data between main memory and the CPU, yeah, it's expensive. I think Professor Mutlu cited a figure like 60% of system energy is spent solely on data movement. So it's expensive, it costs time and energy. But of note, that's not something that the authors emphasized in their paper as a motivation for their design. Okay, so now let's cover some background. The only thing you really need to know is what SIMD parallelism is. So this is a diagram from Flynn's taxonomy. SIMD means single instruction, multiple data. And so we're talking about one instruction distributed among many execution units who all operate on separate small pieces of data. That was kind of the only thing you needed to know. So I thought in the background, I'd also toss in a timeline of some benchmark or flagship processing and memory papers. So you can see down at this end, we have these two kind of closely lumped papers that a lot of the later papers cite in 69 and 1970. And then we have this sort of 20-year gap in the literature. And there were some papers, but they weren't really super influential or well fleshed out. And then we have like kind of a boom of processing memory in the mid to late 90s. And then in the early 2000s, things kind of taper off again until 2013-ish, and then we see a lot more processing and memory literature. And I'd like to talk about why when we get to the discussion section. Okay, so now let's cover the hardware implementation that the authors did in this paper. So this is kind of an overview of the system that they created. So they have this Spark 2 host station, which isn't itself a supercomputer, but it was certainly a high-end computer in 1995. And then everything in the dotted lines is the processing and memory subsystem that they created to interface with it. So the key components in which we're going to cover in depth are the Terasys interface board, the PIM array unit. Within each array unit, we have a certain number of PIM chips, and within each chip, there is a processor or many processors, 64. And then we're going to talk about how the processors are able to communicate with each other via communication networks. Those specifically are the global OR, partitioned OR, and parallel prefix networks, and we'll have an example of how all of those work. Okay, so starting with this interface board, it interprets instructions from the host system. Basically, the most significant bits of instructions sent to the PIM unit are informing the Terasys interface board of whether the instruction is a PIM command or just a regular read or write, because the PIM array is capable of functioning both as conventional memory or as a processing memory array. And yeah, the authors were able to make this process a little bit faster by doubling the issue rate by including 2 PIM commands per instruction. That's just an implementation detail. And the Terasys interface board also handles conditional execution among the PIM units via the global OR network, which we'll touch on later. Okay, so what do the actual PIM array units look like? Well, if you imagine this is one such array unit, it consists actually of 2 boards. And in total, there are 8 banks, and each of the 8 banks has 8 PIM chips, and then each chip has like some certain architecture, which we'll cover now. So this is what an individual PIM chip looks like. As you can see, it's structured as this sort of 2K by 64-bit array, and it has 2 modes. So in conventional mode, the chunks are 4-bit addressable, and we have 32K of them. So this is when you're using the PIM chip solely as a memory array. In PIM mode, we're talking about 2K 64-bit addressable chunks. And in this mode, one processor operates on 1 bit of the selected row. So that's kind of that SIMD parallelism aspect coming into play. And each processor is capable of reading or writing these global communication networks, which we'll touch on in a little bit here. Of note, this chip is said to be 1 million transistors on 1 micron technology. And I thought, you know, why not look up what other technology was using in 1995? And so chips back then had about in the order of millions of transistors, and they were on 0.5 micron technology. And of course, now we're in the tens of billions or hundreds of billions of transistors per chip on 5-nanometer process. So technology's come a long way for sure. Now let's take a look at the actual PIM processor. So this is a pretty involved schematic diagram, I guess. There's not a whole lot to note here. If you guys have questions, we can come back to this later. But yeah, this is the anatomy of one of those individual processors, of which there are 64 per chip. Okay, so the global OR network. This allows the array of processors, or all of the arrays of processors, to return a single bit to the host. And so if you imagine that each of these is its own PIM chip, what happens is that we take the OR across 1 row across all of the chips. So every processor takes its bit of the selected row and ORs it with all of the other processors, and then we get 1 bit. And it's kind of used for global communication in the sense of once one processor has done a task, maybe it can put a 1 in its row, and then all the other processors will know, okay, this guy's found what we're looking for. The partitioned OR is similar to the global OR. So again, we have the same kind of example setup, except now we're computing the OR and recirculating it within a partition of processors. And so a partition can consist of 2 processors, 4, 8, 16, any power of 2, all the way up to the entire system. And so, yeah, the processors within a partition will look at their selected row, and they'll compute the OR among all of their bits, and then they'll be able to recirculate that and use it for control flow decisions, whatever. Next, we have the parallel prefix network. The main purpose of this is as sort of a nearest neighbor communication network, which is how it operates at level 0. It has 15 levels, and the operation can be a little bit hard to conceptualize, so I have sort of a graphic prepared. So imagine we have 6 processors, and each one of them has access to some information from one of the bits in their column of 2K. So yeah, processor 0 has information A, processor 1 has information B, so on and so forth. At level 0, what's allowed to happen with the parallel prefix network is that each of them can share their information with their left neighbor. Then at the next level, now all of them have seen kind of the information of their left neighbor. Even numbered processors are able to communicate with their 2 left neighbors. So now processor 0 gets access to the information from processor 2, and processor 4 gets access to the information from processor 6, so on and so forth. And now you can see that the even numbered processors after level 2 have access to the information that started on their 3 rightmost neighbors. So it's the same for processor 2. It had information that started over here. And so you can imagine how, as we increase the level of the parallel prefix network, we can actually aggregate the information from all of the processors onto one. But that level is kind of selectable. So then as for unstructured interprocessor communication, so it's kind of any-to-any communication, is there any hardware support? No, and it's expensive. So you have to follow the typical paradigm, which is really costly in today's systems, where you have to move stuff from the processing memory all the way to the host system, propagate it around, transpose it, and send it back. So we try to avoid that. Okay, now we'll briefly give you a crash course on the high-level language implementation. Don't feel the need to pay too close attention here. This won't be in the quiz. So the main difference between the variant of C that they program to interface with their PIM array and regular C, I'm just going to step through those. First of all, they have the poly keyword, which designates a parallel variable, which is instantiated across multiple processors. Then, the main kind of primitive type that they use for this parallel programming is a bit field. As we mentioned, the processor bit serial, and so everything is kind of in terms of bit streams. Of note, parallel variables can be composed as with any other regular C type. So you can make structs out of them, you can make arrays out of them, so on and so forth. Functions don't need to know the length of the bit stream you pass them. You can just say, I'm going to pass you a parallel bit stream and give it a question mark. And then, they have this kind of futuristic Python slicing or MATLAB slicing notation. So you can access certain bits of variables with this colon operator. And then they also have this plus colon operator, which specifies a start index plus a bit length. Here's a code example. Again, you don't have to pay too close attention here. I just wanted to highlight a couple more features of the language implementation. So control constructs are parallel when their guard is parallel. In this case, this int1 is a poly bit stream as it's defined up here. So wide int is a poly variable, int1 is a wide int. And so this while loop is a parallel while loop executed across many processors. And then you can have interleaved serial control constructs based on the guard expression of that control construct. So in this case, we just have a regular int in the for loop, bits per divide. And so this control construct is parallel. All of this boils down to, or at least the takeaway that I took from this high-level implementation, is that the programmer is responsible for a lot of optimization. Which is probably nothing new to anyone who's programmed in any kind of C variant. But a lot of it comes down to what you as the programmer do. Okay, brief note on compilation. This language compiles to generic SIMD assembly, which maps to multiple platforms. And for this specific workstation, the authors created a microcode library that implements some efficient versions of common functions. So things like arithmetic and logic operations, random number generation, scans, communication, so on and so forth. So there's some optimization in place, but it's at the microcode level. Okay, what were the results? Well, of note, the authors didn't actually have any figures or anything like that in the paper. So I kind of took these results from the text and then tabulated them and also restated some of the key statements. So yeah, I mean, apparently in a representative tree search application, the authors were able to achieve 8 times Cray YMP performance, where Cray YMP is a supercomputer of the time. And in pseudo-random number generation, they achieved 20 times the supercomputer's performance. They stated that the theoretical increase was up to 50 times, and they said that they compared against real measured figures or best case estimates. Keep in mind that this system that they're testing on and using to compare with the supercomputer wasn't a supercomputer itself. It just implemented a lot of these PIM arrays and then used a pretty beastly workstation. Okay, and this is a specific application that the paper highlighted and that actually sparked another paper following this paper. Apparently, radiologists usually look at 2 different MRI images. The paper didn't provide a figure, so I found these from the internet. I hope that this is what the authors were getting at. Apparently, one is supposed to have better contrast and one is supposed to have better shape and fine detail. So these are T1 and T2 weighted scans. And what the authors were able to do was create an application that allowed you to take subsections of both the images and then superimpose them without losing information via some further methodology, which is covered in another paper. But if you guys want to talk about that in the end, we can. So yeah, and they were able to do this in real time, which apparently was significant at the time. Next, the cost. So the station was assembled by 10 people over 2 years. And some of the components, specifically the boards, were built in-house. And then a lot of the chips were fabricated at a silicon foundry. The conservative estimate from the paper of the cost of the entire station was 42,000 USD in 1995, which, quick math, is 75,000 francs today. And the supercomputer against which they were comparing was 5 million USD in 1995, or around 9 million francs today. So they achieved, certainly performance at a much lower cost. Their outlook in 1995 was to actually combine their PIM array with the next generation supercomputer, the Cray 3. And yeah, some components of the Cray 3 were going to make the whole system, a lot better. Better issue rates, apparently better efficiency of communication among PIM processors due to this gather-scatter hardware. And yeah, the authors speculated that they would be able to achieve petabit op computation. Okay, now I think is the time for any questions. Clarification questions, no? Cool. Then let's talk about the strengths and weaknesses of the paper as I perceive them. So first of all, I would say that the paper was ahead of its time. Although the authors didn't cite the data bottleneck as their primary concern or motivation for creating this workstation, obviously that's a major consideration today, and the architecture that they designed is, I would say, at least a little bit still relevant. So yeah, it was ahead of its time, which is easy to say looking back. And then they created the adaptable hardware design that they were after. So their memory chip is able to act both as conventional memory or a PIM array. And then they provided this high-level C implementation for interfacing with their design. And then they demonstrated the effectiveness of PIM to improve performance even over a supercomputer and then later in supercomputing. As for the weaknesses, maybe I'm a bit nitpicky here, but I picked out quite a few. So the paper itself, although it was mostly an explanation of the processor functionality and features, I would say that the explanation was relatively poor. It was a little bit difficult to follow, and it took some thinking on my part for sure. Of course, the paper is dated, which is easy to say about a paper from 1995. Obviously, the design and the architecture and the process that was used to create their workstation are all dated now, and so it's not directly applicable. I would say that the implementation was expensive for commodity adoption, so it certainly wasn't something that the regular person was going to implement into their home computer. And they used a lot of built-in-house components, which ties into the next weakness. I would say that the paper had limited replicability, and I think that an important part of the scientific method is being able to reproduce results from papers that you read. And so because a lot of the information is staying within Terasys, it's difficult for other scientists to take a crack at it. Then I would say the benchmark selection was poor. As I mentioned, the results were kind of just given in text, and they only really compared against one supercomputer. I think it would have been interesting to compare against other supercomputers or against other relevant designs in the processing and memory workspace. And then, yeah, because their high-level C implementation kind of requires the programmer to, implement a lot of optimizations, you wouldn't be able to recompile existing programs to run on the architecture that the authors designed. It would require rewriting code, which is always a problem for adoption. And then they use SRAM instead of DRAM. Obviously now the commodity is DRAM. So I thought maybe that was a limitation. Finally, let's go on to the discussion. But before we do, I thought it would be interesting to just revisit the PIM chronology from the beginning in a little bit more depth. And yeah, I guess my first question to you guys, unless there are any questions from, no? Okay, my first question to you guys would be, why do you think that there is this gap from, the late 60s, early 70s until the kind of early 90s in processing and memory designs? Because of advances?
Because of maybe the advances in logic technology, so this took a backseat.
Yeah. So actually, that's kind of the main thing that I perceived as well, is that things got faster, and so there wasn't a need for processing and memory in that sort of interim. Let's take a closer look at some of these papers. So this is kind of like the first paper in 1969 that, I don't know, started the PIM movement maybe. I mean, these are just some notes about it. It came up with a design for self-sorting memory. This is kind of the paper that a lot of people cite as the beginning of the movement, where this author noticed that the IBM computer implemented this caching with a microelectric array to support its like magnetic main memory. So he said, why stop at just caching? Why not implement some logic there? And his reasoning was that the number of logic gates on a chip doesn't influence the price as much as the number of pins. And so, we should use the cache as a functional unit. This paper is from Canada in 1992, so just before this paper. This is an interesting figure, I think. And I think that this is kind of the aspect of processing and memory that authors today really aim to exploit, which is the high internal bandwidth of DRAM. And so the bandwidth that's made available off chip is quite minimal in comparison to what's available within the DRAM itself. Then we had this paper. And then we had this paper, which has an interesting figure kind of relating to what you just said. So the gap between processor and memory in terms of performance, I mean, it was always there and it was always growing, but right before 1990, it started to grow even faster. And I think that that's kind of what sparked the renewed interest in processing and memory architectures in the early and mid 90s. This is kind of a related question. Where did the idea of compute-capable RAM go, or even processing and memory? So since 1995, has there been other research? If not, why? What do you guys think?
I mean, we've heard now in the seminar about row clone, but also I think I've heard about memristors being like a primary candidate for computed memory architectures, and a couple of other new memory technologies that are quite interesting for exploiting this compute-capable RAM.
Yeah, and you're exactly right. My answer to this was nowhere. So it's still a prevalent idea. I mean, these are papers following the paper that I studied. And then, yeah, I actually have row clone on here. So yeah, okay. Then my next question would be, if this research body is rich and people are still studying it, why isn't processing in memory omnipresent in commodity memory? So yeah, I mean, you guys all have computers. How come your computer's RAM isn't doing some of the processing for your processor as it is now?
I think one of the biggest factor for actually like common use is manufacturing, because the processes used to manufacture DRAM chips is quite different from actual IC circuits. So you either need to get some sort of like logic units into the DRAM manufacturing processing, or use some sort of advanced packaging. I think that recently kind of gets bigger and bigger, which might get then adoption, where you can actually slice together both DRAM chips and classical IC, basically logic layers. But I think since that manufacturing process wasn't honed out, you couldn't actually manufacture it large scale.
Yeah, I agree. I think that, yeah, manufacturing is definitely a concern. Any other ideas?
I think it's also like a huge shift, because you've thought about computing in logic for so long, and then you need to change everything that you've built all along to suit something entirely different, or at least mildly different.
Yeah, I mean, in terms of, yeah, like how you're going to program something like this, yeah, backwards compatibility for sure. Any other ideas? Nope. Okay. Yeah, so I had a couple of reasons. Yeah, ease of programmability, backwards compatibility, cost, which comes into manufacturing, flexibility. So yeah, I mean, if you put processors on a memory array, like or into DRAM, that's going to take up space. It's going to take energy. How often are you going to be able to make use of the processors there? And is that trade-off of, yeah, extra energy, extra space on the chip worth the benefit that you get in computing? Some people would say no. And I think that this question is kind of a big motivator for, yeah, I mean, is a deep cache hierarchy enough? And I think that it's another form of saying, if it ain't broke, don't fix it. And so I think that motivates a lot of design in engineering, and yeah, specifically in engineering. Like, it's difficult to change a paradigm if something is perceived to be working. And so I think that a big reason why we don't see commodity DRAM adopting PIM is because people don't perceive it, or maybe the research body hasn't made it a big enough issue for, yeah, the big companies that manufacture RAM. Okay. This is kind of an interesting one. Do you guys draw any parallels between what I just explained to you about, yeah, this SIMD parallel memory array and anything in modern computing? I kind of have one idea in mind, but maybe a high-level C implementation. Does it sound kind of like something maybe you guys have worked with before? Nothing in particular? Okay. I drew parallels to, yeah, GPUs. Reading this paper and like going through their high-level C implementation, and then like, yeah, I don't know. It just reminded me of learning how to program like an NVIDIA GPU and CUDA C. Okay. Lastly, I would ask, what applications are well suited to, yeah, designs like this? And I have some tips for you guys, like what characteristics you'd look for in an application in order to propose it as something for which an architecture like this would be useful. Any ideas?
So I think in general, all applications that are sort of embarrassingly parallel are very good, because, and this is also sort of a criticism I'd have of the paper, of the workload selection that you already mentioned. Like, for example, tree traversal, I guess, is sort of parallel already, or let's say matrix multiplication.
Yeah.
But once you get into parallel programming, synchronization, that's all really hard, and probably the overhead is also complicated to manage or not worth it.
Yeah, I would agree completely. Yeah, any other thoughts? No? Okay, then yeah, I mean, what the authors of the paper said were good applications for their design are DNA sequence matching, image processing, tridiagonal solvers, matrix algorithms. So these things that are inherently very easy to parallelize. And yeah, that's the end of my presentation. So any other questions? No? Cool, thank you.
Okay, let's take 5 minutes break. Then we will start the second presentation.
We usually use this limited laptop, so if you can send your slides to me, I can just put it up there. Or you could also join us Zoom, but I guess it would be easier this way.